Have you ever wondered why an apple falls from a tree and why it doesn't just float away? This seemingly simple question puzzled great minds for centuries and led to the discovery of the fundamental force we know as gravity. Picture this: an apple falls from a tree, a scene that inspired Sir Isaac Newton in the 17th century to delve into the mysteries of the physical world. Newton's understanding of gravity presented it as a force that pulls objects towards each other, a force that keeps our feet firmly planted on the ground and the planets orbiting the sun. Without gravity, life as we know it would be quite different. There'd be no structure, no order. We'd be floating around aimlessly like astronauts in space. Picture trying to catch a bus or make a cup of tea in a world without gravity. Complicated, right? This force, so crucial to our existence, yet so often taken for granted, shapes our daily life in countless ways. But the story of gravity doesn't end there. Enter the world of Albert Einstein. In the early 20th century, Einstein proposed a radical reinterpretation of gravity. He suggested that gravity isn't just a force acting between objects, but a warping of space and time itself by massive objects. This theory, known as General Relativity, revolutionized our understanding of gravity and the universe as a whole. Imagine a bowling ball placed on a trampoline. The weight of the ball causes the trampoline to sag, creating a depression around it. If you then roll a marble onto the trampoline, it would roll towards the bowling ball, not because of a mysterious force pulling it, but due to the curvature of the trampoline caused by the bowling ball. That's a simplified view of what general relativity proposes about gravity. But what if we told you gravity isn't just a force pulling objects together? Welcome to the world of general relativity. Get ready, because we're about to dive deep into the enigma of gravity, where things aren't always as they seem. Let's explore this fascinating world together. Imagine a world where time slows down when you move faster. Sounds like science fiction, doesn't it? But it's not. It's reality according to Einstein's theory of general relativity. Our protagonist in this revolutionary idea is none other than Albert Einstein, a man whose name has become synonymous with genius. In the early 20th century, Einstein proposed a theory that would forever change our understanding of the universe, the theory of general relativity. Before Einstein, gravity was seen as a force that objects exert on each other, according to Sir Isaac Newton. But Einstein, with his radical mind, proposed something completely different. He suggested that what we perceive as gravity is in fact the curvature of space-time. Now let's break this down a bit. What is space-time? Well, it's exactly what it sounds like, a four-dimensional framework that combines the three dimensions of space with the one dimension of time. And according to Einstein, this space-time isn't a flat stage where events play out, but can be curved and warped by the presence of matter and energy. Consider a bowling ball placed on a trampoline. The weight of the ball causes the trampoline to curve or dip. Now, if we roll a marble along the edge of the trampoline, it's going to move towards the bowling ball, not because the ball exerts a force on the marble, but because of the curve in the trampoline's surface. This is how Einstein viewed gravity, not as a force, but as a result of the curvature of space-time caused by mass and energy. And just as the trampoline's surface changes with the weight of the bowling ball, space-time changes with the presence of large amounts of mass or energy. This means that the universe isn't a fixed stage, but a dynamic, ever-changing entity, with matter and energy shaping the very fabric of reality. So according to Einstein, gravity is actually the result of this curvature of space-time. Intriguing, isn't it? Einstein's theory, as revolutionary as it was, needed proof. And the proof came from the stars. Just like any scientific theory, general relativity had to withstand the rigorous test of empirical evidence. This is where English astronomer Arthur Eddington steps into our story. In the year 1919, the world held its breath as Eddington and his team journeyed to the island of Príncipe off the West African coast and Sobral in Brazil. They were on a mission to observe a total solar eclipse. Now you might be wondering, what does a solar eclipse have to do with general relativity? Well, the answer lies in the bending of light. Einstein's theory predicted that the path of light should be curved by massive objects. In other words, a star's light, when passing close to the sun, should be deflected slightly due to the sun's gravity. This effect, however, is extremely small and only detectable during a solar eclipse, when stars appear near the sun in the sky. During the eclipse, Eddington observed the position of stars near the sun and compared it to their normal position in the night sky. And guess what? The stars were indeed seen to shift, their light bending exactly as general relativity predicted. This moment was a turning point. It was the first major confirmation of Einstein's theory. The results were published in the Philosophical Transactions of the Royal Society in November of the same year, and the world was astounded. The front page of the Times of London read, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." This bending of starlight was exactly what Einstein's theory predicted, catapulting general relativity from theory to reality. Suddenly, the universe was not as it seemed. It was far more mysterious, warped and curved by the very fabric of space and time. And all of this, illuminated by the light of distant stars. You might think, great, but what does this have to do with me? Well, you might be surprised. Let's talk about global positioning systems, or GPS for short. These handy devices have become integral to our daily lives, helping us navigate unfamiliar routes, track our fitness routines, and even allowing our smartphones to know exactly where we are. But did you know that the accuracy of GPS technology relies heavily on the principles of general relativity? To understand this, let's take a quick trip to space. GPS works by using a network of satellites that orbit the Earth. These satellites send signals to your GPS device, which then calculates your precise location based on the time it takes for the signals to reach you. Now here's where Einstein enters the scene. According to his theory of general relativity, the presence of mass and energy distorts the fabric of space-time. This distortion affects the passage of time, with clocks ticking slower in stronger gravitational fields. This is known as time dilation. In the case of our GPS satellites, they're far from the Earth's surface and hence in a weaker gravitational field as compared to us on the ground. Consequently, the clocks on these satellites tick faster than our watches here on Earth. If we didn't account for this, our GPS locations would be off by several kilometers. Isn't it fascinating that Einstein's abstract theory of space-time curvature has such a practical impact on our lives? It's not just GPS either. Satellite communication, space travel, even the accurate timekeeping of atomic clocks all hinge on the principles of general relativity. So, the next time you pull up a map on your phone or strap on a fitness tracker, remember that these everyday conveniences wouldn't be possible without the incredible insights of a physicist who lived over a century ago. Next time you use your GPS, remember it's accurate because of Einstein's theory of general relativity. As enlightening as general relativity is, it also opens up a Pandora's box of mysteries. Despite the leaps and bounds we've made with Einstein's theory, it's also presented us with fresh puzzles that have left even the brightest minds scratching their heads. Let's delve into some of these unsolved mysteries and challenges that are as fascinating as they are perplexing. First on our list of enigmas is the concept of black holes. These are regions of space-time where gravity is so strong that nothing, not even light, can escape. But what's truly mind-boggling is the idea of singularity at the center of a black hole. This is a point where the laws of physics as we know them cease to apply, a point of infinite density. How can we reconcile this with our current understanding? This is a question that continues to stump scientists today. Next, we venture into the realm of the unseen with dark matter and dark energy. These are two of the most elusive and mysterious components of our universe. Dark matter, an invisible substance, is believed to make up about 85% of the matter in the universe. And dark energy? It's thought to be the force behind the universe's accelerating expansion. But despite their significant roles, both remain undetected and their nature unexplained. The theory of general relativity, as revolutionary as it is, doesn't quite fit with quantum mechanics, the other pillar of modern physics. This clash between the immense and the minuscule, the cosmic and the quantum, is one of the greatest challenges in theoretical physics. Moreover, general relativity predicts the existence of gravitational waves, ripples in space-time caused by accelerating masses. While we've managed to detect these waves, we're still in the early stages of understanding their full implications. While general relativity has reshaped our understanding of the universe, it remains a field ripe with unanswered questions. Unraveling these mysteries might require a new scientific revolution, a shift in perspective as profound as the one brought about by Einstein's theory. And who knows, perhaps you'll be the one to crack these cosmic conundrums. From bending starlight to bending time, general relativity has revolutionized our understanding of the universe. But what does the future hold? As we gaze into the future, we see a realm of possibilities where general relativity could hold the key to unlocking the mysteries of the cosmos. We are standing at the precipice of a new era where the theories of today could become the realities of tomorrow. One exciting frontier is space travel. General relativity could provide a roadmap for exploring the stars in ways we've only dreamed of. It might sound like science fiction now, but imagine a world where we can harness the power of black holes for propulsion, or use the curvature of space-time to shorten our journeys across the cosmos. These may seem far-fetched, but they're potential applications of Einstein's equations waiting to be explored. Beyond space travel, general relativity could also revolutionize our understanding of the universe itself. It could help us decode the cryptic language of dark matter and dark energy, the elusive substances that make up the majority of our universe, yet remain largely invisible and undetectable. By embracing the principles of general relativity, we could shed light on these cosmic shadows and reveal the true nature of the universe. But perhaps the most intriguing potential lies in the unification of physics. For years, scientists have been searching for a theory of everything, a single framework that elegantly combines general relativity's grasp of the macroscopic universe with quantum mechanics' understanding of the microscopic world. If we can bridge this gap, we would achieve a monumental breakthrough, reshaping our perception of reality. So, the future of general relativity is bright and brimming with potential. It promises to guide us on a journey of discovery, pushing the boundaries of our knowledge and challenging our understanding of the universe. As we continue to explore the cosmos, who knows what further mysteries general relativity might help unravel? So, what do we know about the theory of general relativity? We've journeyed through the Enigma of Gravity, from its mysterious nature to the revolutionary idea that redefined our understanding of the universe. Einstein's general theory of relativity, a product of 10 years of relentless work, presented a new perspective on gravity. It's not just a force, but a curvature in the fabric of space-time caused by mass and energy. We've seen how the theory was proven, against all odds, during the total solar eclipse of 1919. The bending of light around the sun, predicted by Einstein, was observed and measured, cementing the theory's place in the annals of scientific achievement. Our exploration took us through the surprising ways general relativity affects our daily life. Precise GPS navigation, accurate timekeeping, even the understanding of Earth's age, all owe a debt to this magnificent theory. It's not just about grand cosmic phenomena, it's intertwined with our everyday existence. We've also delved into the challenges and unsolved mysteries that keep scientists on their toes. The elusive dark matter, the enigmatic dark energy, the singularity at the heart of a black hole. All these are areas where general relativity and quantum mechanics clash, sparking fascinating debates and driving our quest for a unified theory. And finally, we've glimpsed at the future potentials this theory holds. From the possibility of time travel and wormholes to the study of the universe's origins and its ultimate fate, general relativity continues to guide us on an exciting cosmic adventure. In the grand scheme of the universe, we might seem insignificant, but with theories like general relativity, we continue to unravel the mysteries of the cosmos. Until next time, keep wondering and keep exploring.